you have to do is sit down and do it. And unless you do it, no matter again as usual, and it is even true here, that this listening will have no impact. Okay? Actually, there is now it's a good time to say that. So, did you hear the news that Deepak Dhar won the Boltzmann medal? So, any of you are familiar with this news? Any of you understand what is Boltzmann medal, or any of you understand or know about Deepak Dhar?
No.
News on the
Sorry.
I, we saw the news on ISER newspaper.
Yeah, so Boltzmann medal is the greatest award in statistical mechanics you can have, and it's like the Nobel of statistical mechanics, and he's the first Indian to have it. And w- Deepak Dhar was a faculty in TIFR, and he was throughout for 5 years. Um, I had plenty of interactions with him, meetings, and he was my thesis committee main examiner, etc. Everything. Took a lot of course on him from him also, like lot of things I learned from him, and he's one of the greatest physicists I know. So he had a famous quotation which he told us in a class, that when you hear this Satyanarayan Katha, which means you listen that Satyanarayan Katha 108 times and you get punya and go to heaven, right? That's the deal. But in physics, it's not like Satyanarayan Katha, because even if you listen it 108 times, you won't go in any physicist heaven. So you have to do it yourself. Okay, no, the listening is useless here. Okay, unlike God's name, which you listen and get punya, here you get no punya. So that is what he used to tell us. So it's a good time to share that joke, because now that he's famous among common people. He was anyway famous among experts, but now he's famous among random common people. Okay, so make sure you don't just listen; you also do it. Okay, so now this part, as I said, since the best way to do it is to sit with the calculation and work it out every step in your own hand. And for that, the best strategy will be, mm, so I will give you continuously some pre-recorded lectures, because the pre-recorded lectures have every tiny details worked out, which may or may not be possible. I'll try to do it in the class, but may or may not be possible to do it in the class. This was also one of the things happened, because when I was about to start this chapter during my first semester of quantum mechanics 2 teaching, and my first semester of any teaching, so then the lockdown happened when I was about to start, and so then I prepared all this pre-recorded, and then I realized that I could have never made taught it in this kind of details in the class, because I had this advantage of going uninterrupted for 40. It's not that I'm talking for 2 hours. It's like each class is like pre-recorded lecture. When I'll give you, you'll see they're 45-minute maximum, but yet their content is very high, because all the tiny details are worked out. So I would give you those pre-recorded lectures and the notes, because they are very detailed and all. And I will suggest that the best way to study will be to take that, come to the class, listen to the class actively, understand all the details I'm telling. Then when you study at home, which you must do in this part, sit with that pre-recorded and pause it many many times, understand all the details state, because it is, since it's pre-recorded, it goes a little fast. So pause it many many times, write down it in your own hand, take the notes, make sure you understand all the flow of the calculation, and then you, if you need, you can read the book. I am closely following throughout the this part. I'll follow Sakurai and Griffith, mainly Sakurai, and occasionally Griffith, occasionally Shankar. Then if you read the book, or you, even if you don't necessarily need to read it, but even if you can give a quick read, you will understand everything clearly. So the whole thing will be much more streamlined. You don't need to watch the lecture again, and the actual this live lecture, and better to watch that pre-recorded, because it is much more dense and has much more content. And the other thing is that in this part you may not need to do this, all these derivations I am doing. There are a lot of derivation I will do. You don't need that derivation directly for the purpose of exams here or any other exams, because they are extremely detailed. And nowadays we don't have this kind of questions that derive this formula, which is like a long calculation. But it's important that you know the derivation, because one of the key thing in perturbation theory is that It's a beautiful machinery, which means you start from some as you set up the problem and do some approximation, and you end up with a very cute tiny formula which is easy to remember and easy to use. And then you also come up with the condition that where that formula is applicable. So this final formula and the applicability is the main thing that you need in various exam problems and etc. But how this arrived is extremely useful if you want to be a physicist, because this all these detailed step that how you lead go from this such a difficult problem, how you break down the problem into bite sized pieces, and then you make it like a very nice formula at the end comes out, which any any random person can calculate. Any minimally physics educated person can calculate. So this power of the formalism that you want to experience, that you want to that you need to calculate, and at least once in your lifetime. And then when you develop some other theory in your research or anything, that skill is going to be extremely useful. I mean, this is another reason why people often say that physicists have a very well rounded set of skills, not just and that will not happen if you just learn to use the formula to solve the problem. So I would recommend you to do this part. Don't just listen again like in Deepak Dhar's language. And that is basically my generic advice. So let's now go back to the topic. And I would suggest again that so I hope all of you watched the first pre-recorded lecture I gave you. The first lecture is a very basic overview of perturbation theory. It's not at all technical. It's just give you an idea about how the perturbation theory in general works, where does it come from, what are the basic idea. And there are three main concepts that is discussed in that pre-recorded lecture. Oops. Three main concepts. So let me write it as big O notation, which tells you order of magnitude notation. The second concept is applicability of perturbation theory, which tells you if I have a so the basic idea of perturbation theory is you have a Hamiltonian which you can write it in two parts. Okay, and the two part is like some h naught part where you understand the solution, and h1 is where you don't know the solution, you don't know anything about that solution, and you want to write down the full problem solution in terms of the part that you know. Okay? And in order to do that, you introduce a small parameter here, you call it like some lambda h1, where lambda is a dial that can be tuned from 0 to 1, and this is a small parameter to tackle the problem. It's usually a physical parameter in the problem that you know, and you'll do some examples, but you can use it as a tuning as purpose of tuning, and later you can say okay, this parameter is just to help you to set up the problem. Okay, and actually it's not always all the problems we'll do in a course will have a clear parameter, but in real world it's not always easy to find that small parameter, and that's a very interesting question, that how to deal with that when there is none. So if such a problem exists, then we want to ensure that if I have a set of levels for h naught, then after I turn on the h1, the h I turn on the h0, these levels are not crossing each other. Like this something of this sort is not happening. So let me, a more appropriate picture will be this. So let's say I'm turning on the lambda, and this sort of thing should not happen. This sort of thing should not happen when I reach at h or some finite. So when that happens, then it's a problem, because you cannot track down that which levels are which level. You want to know this level is level 1, level 2, level 3, level 4, and they will remain level 1, level 2, level 3, level 4 after the perturbation. If they crisscross each other, then it's a problem, and that is actually a very interesting class of problems of level when the levels cross each other. So that led to a condition. So we gave a condition, and the condition is these levels, some ei to ei plus 1, a pair of level must be much less than the v or b or h1, that perturbation. So we landed on that conclusion. Sorry, it's the other way. Okay. So if the perturbation is so big that two levels starts mixing with each other, then the perturbation theory fails. So we gave an intuitive reason, and we gave an example using a two-level system. But the proper reason will work out today, the proper a more rigorous derivation. So that was one of the main point, and we called it the no level crossing uh, theorem. So this was one of the main point, and then we gave an example of a two-state system. We didn't give the example exactly in terms of perturbation. We just said there is a two-state system, and let's say there is a an extra h1 is applied on that in that Hamiltonian, and what kind of Hamilton strength of that potential will lead to this kind of condition. And since the whole problem is a 2 by 2 matrix two-state problem, you don't actually need perturbation theory. You can do the whole problem exactly, and then you can also do it using perturbation theory and compare if your formalism is correct. So that was the purpose of that exercise. So this was basically a quick overview of the pre-recorded lecture. So now let's just develop this perturbation theory much more formally. So in order to,
So
yeah,
does it like you do those energy levels? What does it mean when you're like drawing them, changing and slanting and stuff? These are energy levels, right?
yeah. So what I'm saying, let's say there you have a bunch of energy levels, and I am tuning the lambda. Okay, this is my full problem, right? So if I increase my lambda to some desired lambda star, let's say that is my problem I want to solve. Now for changing the 0 to lambda star, I'm plotting the energy levels against that. Okay? So crisscrossing means at some point of time two levels becomes equal, and then they cross each other. Okay, you
At
see what I'm saying?
some
Yeah, so at some lambda there is a particular lambda. So let's say this is my starting point, 1 2 3 4.
these are
And
energy versus lambda plots, right?
yes, energy levels, En. 1 2 3 4 means En. So 1 3 2 4. At the end I reached on 1 3 2 4. Okay? Because these levels crossed each other at some point of time.
Okay, so they change and they okay, got it.
Yeah, but this picture has a problem, because and problem means it's very unlikely to happen in most problem, but in some problem that can happen, and then it is very interesting, because if these levels have to crisscross each other, then there must be a particular lambda where these two levels are exactly same. Okay, you see what I'm saying?
Yeah.
But that means there is a degeneracy, but degeneracy doesn't come without a symmetry. Okay? So that means you have, for a particular value of lambda, the system has a symmetry.
Hmm.
That's very unlikely to happen, but it happens in certain problem, and it requires fine tuning. That also means it requires fine tuning. Okay? Fine tuning means it depends on very precise value of a particular parameter.
Hmm.
So this kind of some accidental symmetry is required, and that is very unlikely to happen to most problems. So that's why this no level crossing theorem is applicable in almost all the problems we know. Okay? But there are exceptions which are very interesting topics that I'll come later. Okay? Actually, I will not come in the course, but I'll mention it to you. Maybe you can look it up. Okay, so now that this I set up the premises of the problem, so now let's go to the formalism. Okay, the formalism is actually quite easy. So we want to solve. So let's say this is a problem we know. This is the n0, and en0 means it's the h0 eigenvalue. and this is my unperturbed problem. And let's say I have ordered the states according to their increasing value, and I want to focus for time being on non-degenerate states. The whole problem is non-degenerate. When degeneracy comes, that we'll discuss that next. Okay. So non-degenerate state, that means I can write all the states as like en minus 1 0. There is no equal. Okay. In other words, this en 0. Actually, let me just say there can be equality, but not here. So I am interested in showing you the perturbation for these some levels. So the nth level. So nth level at least should not be degenerate. Elsewhere there can be degeneracy. So there is no equal to sign here, all less than. Okay. When the degeneracy comes, then it's a problem, and that we'll discuss. So I think in first lecture I used the notation not lambda, I used epsilon. So I'll stick to epsilon. Although Sakurai notation is lambda, 0 to epsilon. So let me remove the lambdas and make them epsilon. But then there is a problem that this e's have to be e. Okay. So now in this notation, here the eigenstate of the whole problem is some n naught, and here the problem is h epsilon n epsilon equal to e n epsilon. Okay. And also we demand that the perturbation is the epsilon dependent perturbation is of the form of this. It is not always true. Not always you can write it like that. And when you cannot, then you cannot do perturbation. So this is my equation 1. I mean, you cannot do perturbation theory in this form. There are many forms of perturbation theory. This particular form is called Rayleigh-Schrodinger perturbation theory, what we are learning here. So this is epsilon equal to 0, and En at epsilon equal to 0 is En naught. Okay, so now I define a quantity called delta n. So what is delta n? Delta n is nothing but the correction in nth level. So En0 is the eigenstates or eigenenergies of the unperturbed problem, and En is the eigenenergy, En epsilon is the eigenenergy of the perturbed problem, and their difference is called delta n. So this is the correction energy shift of the nth level as epsilon is changed from 0. Okay. So that means I can rewrite my equation, this equation. So I want to express equation 2 as in terms of unperturbed problem. So this is my equation 2. I want to use these 2 and 3 to rewrite the 2 in terms of the unperturbed problem. So what I can do, I can remove the epsilon h1 to this side and rewrite it as en0 minus h naught n equal to epsilon h1 minus grad n. So all I did is I just took this, introduce the delta inside it. So delta is delta plus en naught, and this side is all. So the one of my agenda was, oops, what happened? My agenda was to rewrite the equation in a way that one side I have all the unperturbed quantity. Okay. So this is my this form. And then at this point you might want to revert this equation, and the reason is you want it to be written in this form. But this might not be very useful yet, because what is happening in this equation, what you want to actually calculate is this guy and this guy, and what you want to calculate is appearing is both side of the equation. So then it is not a very useful thing to do, but you know what to do in such kind of scenarios. These are called these transcendental forms. So you have to write this equation, solve it self consistently. It means you start with a trial solution in naught and delta n naught. I plug it in there, you work out some n, and then you plug it back here. So start with the trial solution in naught, plug it here, you work out some n1, then plug it back here, then you get some n2 and plug it back here, and you keep doing it until these two sides converge. Okay, that is what we are going to do, but a little systematically. Okay? But one more problem is, in order to write this equation, one more problem in writing this equation in this form, we have to guarantee that this quantity exists. And this quantity cannot exist if it is acting on a n naught state. Okay? Why? Because E n naught minus H naught acting on a n naught state is not well defined, because this will give you 0 on this side. Okay? 0 in the denominator, so it is not well defined. So how to rescue from that situation? That notice that this guy, this n naught, this whole object, this epsilon h1 minus delta n has no component along naught.
Sir,
Yeah,
En0 indicates for nth level it's zeroth order correction.
yeah, that means nth level of the unperturbed problem.
Okay.
Yeah. So how can you show from here? Can you show the statement that that epsilon h1 minus grad n has no component along n naught? If that is true, then you are safe. Then you can apply that inverse operator. Okay, can you show this much? So this equation, so this side en naught minus h naught n. What to do? So if I can do this and show this to be 0, then we are done. Then that implies this is also true. So if this is true, then this guy has no component along n naught, okay? Because the matrix element with n naught is 0. Are you following? Are you with me? Or you're lost?
What is N naught?
Oh my god. N naught are the eigengates of unperturbed problem.
But how can you divide by an operator?
Huh? What do you mean by that? Where did I divide by an operator?
Here in En naught minus H naught. Because H
You
naught,
you, you are saying this one?
yeah,
Did you ever heard of matrix inverse?
yeah, but okay. Right.
So what is this En naught minus H naught? It's a matrix inverse, right?
Yeah,
Okay, makes sense?
yeah.
Okay. Now, can you show this? That I want this to be true. And I'm claiming that this is always true. But can you show this? And you know, to show this, all you have to show is this. Do you think this is true? What happened? Are you all sleeping, or it's too much for early morning?
Sir, as the energy levels are shifted, being so there is a dependency of wave function on that energy. So it can be
No,
zero.
you thought too hard. This is very trivial.
Okay.
What is H naught acting on N naught? It is En naught minus En
Yeah,
naught.
not. Yeah.
So it is zero.
Yeah.
Trivially
Yeah.
zero. That's why I asked you the trivial thing, because otherwise it's too much for early morning. But even that is turning out to be very, very non-trivial. Okay. Okay. I have your, I mean, you have my sympathy because it's heavy. Okay. So now let's see now let's see what to do, what can I do to write this equation in a form like this, and then use some self consistency condition to solve it. Okay? So let's define a projection operator. Let's define a projection operator, and the purpose of the projection operator is to project out the nth state. I think there are two ways I can make this part a little better. One way is either I teach on board, then you can see many equations at the same time. In tablet, you cannot see that. Okay? And the other option is I give you the pre-recorded lectures, so you watch it and come to the class. Then the class becomes easy. Okay? I don't know what is the better solution. Let's try out both and see what works. Okay? So I want to define now a projection operator, because otherwise it seems you are not following it in real time. And I understand why it is possibly so, because it's a bit heavy. It's now if it feels heavy, it will get heavier later. So what is this operator? This operator is this guy. So what does it do? Its purpose is to throw away the n naught state. It means it's all the eigenstates of the of the H naught um, Hamiltonian except the n naught. So if I act it on any state, it will project it onto all those states except the n naught. Okay? So now I can define it nicely, because if I use this projection, then En naught minus H naught inverse. So if we don't like division by operator, let me write it as inverse. This is well defined, and this is nothing but so let me write this equation as 5 and this equation as 6. Okay. So then from 4 and 5 I can define. So 4 and 5 means this definition and the fact that this guy is 0. Did I define a 4? No, I didn't define a 4. So the 4 should be defined as this one. So from 4, so 4 tells me that this guy doesn't have any component along n naught, and the phi defines this n naught operator. So from 4 and 5 we can write a phi n epsilon h1 minus delta n in h1 minus delta n. So what did I do here? I did nothing. I just rewrite this with a phi n. So what does phi n does? So if I rewrite the phi n, this is basically k0, oops, k0, k not equal to n, this acting on this guy, acting on this guy. So what is this basically? It is rewriting this whole thing in the E0 basis, in the basis of the unperturbed eigenvalue, unperturbed Hamiltonian. Okay? With because of the projection operator, it guarantees there is no projection on the n0, which is anyways true because we know the n0 n matrix element is 0. Okay? Everybody follows this step? What happened? Why there is so
Yes,
much
sir.
silence? Okay, at least someone is following. Anybody from BSMS? Is there anybody who is not following? I think that is a probably safer question to ask. Everybody is following. Great. Or you are too behind to even say anything. What is the so give me feedback, otherwise how will I know what's going on?
So what is in this empty bracket? Like this is after.
This is this guy.
Okay.
Hello, sir.
Yeah.
Can you again explain what does equation 7 explains?
Yeah. So equation 7, it just tells you that I can rewrite this object with a phi n on this side. So why is so? Because if this object doesn't have any component along n naught. So let me write. Equation 4 tells us that, right? Now I can express this guy with a phi n in the front. So that means nothing but rewriting this equation, rewriting the left hand side, right hand side of this equation in the eigenbasis of the E0 operator. So what does this side means? It is rewriting h1 minus grad n in the eigenbasis of h0. That's all. So that is all I did. So that is the meaning of equation 7. Makes sense?
Yeah.
Okay, good. Keep asking questions. Try to follow it. This is heavy in algebra. Okay, and if you
Sir,
are lost, it's very. I mean, it's okay. I know you can get lost, but still try to stay afloat as long as possible. Yeah. Question.
Can you show the sixth equation once?
Sixth equation. Yes. Sixth equation tells nothing but that if I act this inverse operator on the phi n, then it's a well defined quantity, because k is not equal to n, so this is never going to blow up.
Oh,
So
okay.
also
Thanks.
fourth equation.
Fourth equation. Yeah.
Okay.
So how about, yeah, so from now onward I'll give you something a priori, and that is the advantage of writing in board also, because you can see multiple equations. Anyway, let's try. So that means we want to write now. So now we are inverting. So what was our agenda? Our agenda was to invert this guy. So now I want to invert it in this way. So we know that we can do it because this side doesn't have any component along n naught, but I want to write it explicitly. So I can write now en naught minus h naught in. This is my equation 8. Okay. I just inverted, just did the same thing as before, except I put in the phi n to write it in the basis of h naught operator. But it is still not what we want. Okay. Because this equation is consistent mathematically, but it doesn't satisfy the requirement. We want this to happen also. So as the epsilon goes to 0, we want our n to fall back to n naught. Okay. N is the eigenstate of the full equation, and n naught is the eigenstate of the unperturbed part. Okay. So a delta goes to this means delta n goes to 0 as epsilon goes to 0. So I want that to happen, but that is not happening here. Okay. So then what to do? So in what
This
is
thing
happening?
just for consistency of the equation.
Yeah. So this is, so remember what was our problem? Our problem was we want to solve this. Okay. We want to solve this problem where, so let me box it. Remember what was our problem? We wanted to solve this problem where h0 n0 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 and h epsilon is h plus epsilon h1. So that means, so there is a dial lambda, there is a, sorry, there is a dial epsilon. When I turn it on from 0 to some non-trivial value, some non-zero value, then we go from this H0 to H epsilon problem. And we demand if I dial it back to 0, then I fall back on this problem. Okay. But the way I have written it here, that is not happening, because when my epsilon goes to 0, this term vanishes, this term vanishes, this whole thing vanishes, so it's 0. That is not correct. That is not what we wanted. Make sense?
Yes.
So to fix this, I want to rewrite this as it's a very easy fix. I just added a n naught on it. Okay. So I'm constructing the answered solution. So I just added a n naught here. Okay. So now it is fine. So now if I cut it back, I just need the condition that limit epsilon goes to 0, then epsilon is 1. If I impose this condition, then I have it. Okay. So, and what is this Cn epsilon physically? It is n naught n. So if I sandwich n naught in both sides, this part is this, and this I know has no component along n naught, this, so it will fall to 0. So this is this guy. So it's basically the probability of finding the unperturbed state along the perturbed state n, unperturbed state not along the perturbed state n. So now 9 is has the satisfactory structure we want. Okay. Now later we want to impose another condition that Cn epsilon is n naught n is 1 for all epsilon, not just epsilon goes to 0. Okay. So that means I want to normalize the n naught state, but instead of doing this, so this is what I should have asked for, but instead I am imposing this. Okay. So this we will actually do this at the end, after we solve the whole problem, we'll normalize the n at the end. But at this level, we are just imposing this to make the algebra easier. So we'll impose it.
Sir, can you repeat this point again?
Okay, so what did we learn at this stage? At this stage, we learned that we want this solution to fall to n naught when epsilon goes to 0, but that is not happening. It is falling to 0. So in order to do that, I added a n naught, okay, with the Cn epsilon, and we impose the condition that the Cn epsilon is 1 when epsilon going to 0. Then that means n is n naught when epsilon goes to 0. So this implies n goes to n naught when epsilon goes to 0. So that gives us everything we wanted. But and what is this Cn epsilon physically? It is basically the probability amplitude to find the unperturbed state n along the, when you do a measurement of perturbed state n naught. Sorry, unperturbed state n naught when you do a measurement in the perturbed state n. So this is the physical meaning of this. But now I want to put a more generic condition. So this is a generic condition. A more generic condition compared to that. Let me call it equation 12. And the generic condition, it is not just 1 only when epsilon goes to 0. It is 1 at any epsilon. And this is a superset of that condition, because if this is true, that is true anyways. Okay. Now you might be wondering that why I am doing this, and I am saying this, I am doing this to save algebra. That we'll see immediately now. And at the end, we anyway want the n to be normalized. Okay. N to be normalized, which we are not doing at this level. We'll do it after we finish the whole set up the whole problem, and at the end we'll normalize the n. Okay. Do you follow now?
Yes, sir.
Yeah. So if this Cn is instead of 1, if I wouldn't have done that, it would have been some number, and that we can always take out as a factor. So we know that only the relative phase matter. So that is why it is something without loss of generality we can do. Without loss of generality, we can do by just for saving algebra. Okay. So then my answer looks very neat. Then n is n naught plus phi n en naught minus h naught epsilon h1 minus grad n. Okay. And from 4 and 11 we know that grad n is n naught just to show you what is 11. 11 is this which ensures this much, and 4 is this. Okay. So if I apply on this, so I can write the grad n. I can write it these two sides as n naught epsilon h1 n minus grad n naught n. This is equal to this, and this I set to be 1. So grad n is nothing but n naught h1 n. Okay, that is basically my 13. So let me box it here because it comes from future. Okay, I hope everybody in the same page so far. Okay, so now I want to systematically all we have done so far, we didn't solve anything. We didn't even use any approximation or anything. We just set up the problem in a way such that it gives us the desirable format, which means as epsilon goes to 0, it neatly falls to n naught. And while doing that, we define the h delta n, which is basically the difference between these two states, as a matrix element between the n naught and n of the difference between. So what is epsilon h1? It is basically the difference between the full Hamiltonian and the unperturbed Hamiltonian, and that is what delta n is, except the matrix element is between n naught and n. So now we will like to solve it, and of course we have the definition of phi n. Phi n is basically 1 minus n naught n naught. Okay. So now we want to find a solution. So let me rewrite that. So phi n is k naught equal to n k naught. This was my equation 5. Okay. And now we all together we want to find a self consistency equation. This is the self consistency equation, and solve it for any epsilon that is between 0 to 1. Okay. 0 to 1 actually, because we'll see if it is exactly 1, then you cannot do anything of series solution. So now we will first time apply the perturbation unsuch, which means we expand. So there are two unknowns, right? So that is expand n and delta n. These are our two unknowns in powers of epsilon. Okay. And match the appropriate coefficients. So what does it mean? So it means if I have a Taylor series of this form and I want to expand it around epsilon go to 0, f prime 0 epsilon plus that epsilon independent. So it means if it is of this form, so these terms are epsilon independent. And we know that if we can show this f epsilon is ever equal to 0, then each of these, we know that if I have a polynomial a plus bx square plus cx cube etc equal to 0, then all of them has to be 0. All the coefficient has to be 0, otherwise it cannot happen. So all of them has to be 0. So we are going to use this principle to solve this equation. So this is just a mathematical answer. So now let me write it in terms of our problem. So perturbation unsuch is that Notice that I am writing this as n naught plus epsilon square, but delta n I am writing it epsilon square delta n2 etc. Because actually what I want to write is the full problem solution in terms of e naught en naught plus epsilon en1 plus en2, but the difference will be then epsilon delta n naught epsilon square delta n2. So this is my 15 and this is my 16, and then we plug the 15 and 16. Plug 15 and 16 into 13 and match coefficients. 13 is nothing but this equation. So we'll plug that on such and match coefficient using this idea. Okay. So what happens when you do this? So let me rewrite 13 in the form. Rewrite 13 as this polynomial equal to 0, this kind of form. So this is n minus n naught minus phi n. I'm just taking the right hand side of 13 into left hand side. En naught minus h naught epsilon h1 minus grad n. And all we need to do is plug in the stuff inside, and all the epsilon independent coefficients now had to be 0 because of this idea, from this idea. Okay. So when I do that, so now, so plug 15 and 16 in 17, which is equivalent to 14. Okay. And then we have an equation of the form that f of order, now it's a big O notation, plus, let me write g of order of sine square plus dot 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 0, and it will satisfy each of these terms are 0. Okay. So plug in this, just do this little bit of algebra, and you will see that this will lead to the following. Leading to order epsilon 1. This is something we already know. No, this we don't know yet. Order epsilon 2, epsilon square, and similarly order epsilon n will be okay. So did you understand what you have to do? You have to plug in into these two things, this guy and this guy, plug into this here, and match and set 0 to every coefficient. Okay. Every coefficient of epsilon square, epsilon 1, etc. Okay. When you do that, you get this equality. Why? Because this side you will get this delta n and delta n orders, and then in this side you will get the n naught h1 orders. Okay. And that will give you this set of equations. Everybody in the same page? Following? Am I connected? Are
Yes,
you
sir.
following? Okay, very good. Okay, good. So notice one more thing here. So let me give this equation a name, is equation 18. So for every energy shift of order, so what is this guy? This guy is energy shift. Because delta n is nothing but En minus En0. So delta n1 is the first order epsilon. 1 means order epsilon. Delta n2 is order epsilon square, and so on. Okay. So for every, so now notice there is actually one more catch. So delta n1 is easy to calculate because you know the h naught, you know the h1, everything. You know the n naught, you know the h1. But in order to do delta n2, you need to know the n1 that you don't know yet. You have to solve it. Similarly, for any order, you have to know the previous order n1. Okay. So notice that for each energy shift, we need to know state correction one of a given order one order below. Okay. So that means I can rewrite. So let's try to do that. So we can rewrite now the n as, we know the n is nothing but n1 plus n2 and so on. So this is also can be rewritten as phi n naught minus h naught epsilon h1 n1 and delta n2. I'm writing again the equation 17 or 13. Not 13. What is that equation? 17, 16, 14. I'm rewriting the equation 14 by putting all the terms of delta n. Okay. So then it will become epsilon h1 minus delta n1 plus del square delta n2 and dot 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 times n naught plus epsilon n1 like from 14. This is equation 19. Now again I am doing this, playing the same game, equating powers of epsilon by same argument. We can work out phi n what did I do here? I want to write down the first correction. Okay. Again, I take everything to the left side and I want to set that to be 0. So I will get the first correction to set the coefficient of n1 to be 0. Okay. And what is that coefficient? That coefficient is nothing but phi n e naught h naught. That coefficient is nothing but phi n e naught minus h naught h1 n naught. So then I can rewrite, but I know this to be true, that phi n grad n1 delta n1 n naught is 0 because of the projection. This has no projection along n naught, okay, because phi n is equation 5. So now we can compute from 18 the second correction, because we wanted, remember here what happened, we needed this n1, without that we cannot proceed. We want to express the n1 in terms of things we know, which is n naught, which we did here. So we worked out the n1. So now we can calculate the full expression. This is nothing but h1 phi n e n naught minus h naught h1 n naught. So this is my full expression of delta n2. Okay. So now you can proceed from here. So what I'll do today is I will just write down. I will not go in terms of the normalization. I'll just work out the terms and leave you with some exercise. So now, so knowing delta n2, work out the epsilon squared term of equation 19 using 20. You may not be able to follow at this hour, but let me just write down the result because it's 2 lines of algebra. So what I'm doing here, I'm plugging the expression of delta n2 and the equating the epsilon L square. So it will be two set of equation. This is 20, this is 20. No, this is 21. So this is 22. Okay. Now this is a very compact form. If you notice, this form is very neat and easy to remember. If it is not yet easy for you, let me just write down it in a little tighter notation. So I can now rewrite this whole thing.
Sir,
Yes.
can you please repeat this line? Means I get lost here. The
What?
equation 22.
22. Yeah.
Yes.
So what did I do for 22? So notice what did I do here? You understood this part?
Yes.
Okay. So we are doing the exact same thing at the next order. So we want to know what is this n2. Okay. So in order to know n2, we have to know the n1, the n0, the delta n1 and h1 and all other forms. So we are plugging all of them into this equation, in this equation 19. So in the
Okay.
19, we are plugging this and using
So
20.
to go in next order,
Hmm.
we are using the previous wave functions
Correct.
as well as the energy corrections.
Correct.
Okay.
So if we plug in them all together, you will get these two terms. Okay, so let me just write down the form of the perturbation. Then I leave it here and then you take some time to digest these equations. Then only it will make sense. Okay. So this is En minus En1. So this is the correction. And how this correction look like? This is basically first order is H1Nn. So what is this mean? This means N0 H1N0. This is a short form of this. Okay. Plus epsilon square k not equal to n h1 n k mod square. What does this mean? It means this is n naught h1 k naught. This is the meaning of this notation. En naught minus ek naught plus dot dot dot. So this is the what I learned from here, because if you look at here, these are the corrections. This is the first correction, this is the zeroth correction, this is the second order correction, etc. We can. So I'm just writing all of them together, the full form, because this is nothing but epsilon delta 1 square delta 2. So these terms are just like that. And similarly, I'll write the n, and that's where I'll end the class and have some discussion if you want. So the n naught will be epsilon k naught equal to n k naught. So notice this part, this term is easy because this term is nothing but this. So I'm writing the phi n, expanding the phi n, writing the h1 and in all of them together. So this is k naught h1 en naught minus ek naught. Why it is so? Because this guy acting on k naught give you en naught minus ek naught. This is the first term, which is very easy. Second term is little complicated, but it is still manageable because the way we wrote it is very neat. This is the second term. It has two terms. So it is k naught h1 kl h1 ln en naught minus ek naught en naught minus el naught minus k naught equal to n k naught h1 nn h1 kn k naught square. So your takeaway formula is these two, 22 and 23. So let me, not 22 and 23. So 23 and 24. So this is the state correction and the energy level correction. So try to work out this, try to follow all the sub steps. I'll give you my notes, and also my note means not the board work, my actual note, and also some pre-recorded lectures. So sit down with it, work out all the detailed step such that you understand everything up to 23 and 24. Then we take over from there. Okay. Now questions.
Sir, can you scroll down a little bit, please?
Don't worry, I'll give
Thanks.
you the notes. If you are unable to copy anything in this part, as I said, there is a lot of algebra in this part. If you are unable to copy it in real time, don't worry, I'll give you the notes. In fact, I might give you the notes before the class such that you can follow. Then you don't have to write anything. Okay. So if I missed anything, don't worry, I'll give you everything. Questions? Too lost to ask questions? It's all right if you are not following the algebra, but if you are following the intent and the overall agenda, that is fine. Then you sit down with half an hour and then you'll figure out all the algebra. It's very easy. Okay, if none, that's all for today. I'll see you in the next class, which is tomorrow. And about office hour, so I want the office hour a bit early today because I have to go. I cannot. Last time the office hour went all almost till 7:30. I cannot go that long. So maybe 5. So let me know first if anybody wants an office hour. Then I'll set the time. Maybe I'll move it half an hour on hour. Okay, that's all. If no questions, see you tomorrow.